Hello everyone, I'm Jungle from University of Tokyo, Japan. I'd like to share with you our work about video object annotation. As you know, deep networks require a large amount of training data with crowd truth. However, manually collecting object annotation is a time-consuming task, so it is essential for the development of effective annotation frameworks to generate desired crowd truth for large-scale video datasets. In this paper, we'd like to tackle this problem of video object annotation, where human annotates some examples and then machine learns to generate the remains. Through proposing a novel interactive self-annotation framework, we aim to cut down both time and human labor costs for video object bounding box annotation. This framework consists of two processes. The supported process trains a strong detector adaptively to each video. After that, we put human into an interaction loop between human and machine so that detector can learn modification from human annotator. For the automatic recurrent annotation, our goal is to generate bounding boxes for all objects in videos by letting a detector watch and label videos repeatedly. At each iteration, the detector trend from the previous iteration generates bounding boxes for all videos. We introduced the labeling assistant module to leverage temporal consistency from the videos to filter out these bounding boxes, resulting in new pseudo-crowd-truth bounding boxes for fine-tuning the detector again. The new pseudo-crowd-truth bounding boxes have better quality than crowd-truth at the previous iteration, which leads to the improvement in training the detector for the next iteration. Through the self-supervised learning, the detector can improve itself automatically. We aim to construct pseudo-crowd-truth bounding boxes to train a new detector at each iteration. So we utilize tracking algorithms to reinforce detection results. Each figure presents the entire video where each dot is a detection result in the video. We first eliminate objects with low accuracy score and keep only high confidence objects. After that, tuplets are constructed using deep sort to remove all unstable objects with short temporal length. Remaining objects in a tuplet are then refined to assign a unique label. Finally, we recover accidentally removed objects as well as add missed detected objects using the Siamese tracker. Common average precision metric for object detection only focus on objects of interest without concerning background. They ignore all noise detection, where detected bounding boxes do not touch ground truth. Hence, the metric is not appropriate to evaluate a task of annotation, which considers the global context. So we introduced a new metric called similarity in union for the text. We first convert on detection of an image to a heat map of each category by accumulating score of each object region. After that, we compare two heat maps of prediction and crowd truth using this formula. We also evaluate methods using IOU when binarizing heat maps. We evaluated our automatic process on the cityscapes dataset. We used video sequences from the validation set, which consists of 500 sequences with a total of 15,000 video frames. Each video sequence had 30 frames. To measure the ability of our method in annotation, we performed the cross-domain evaluation for different methods. We train faster RCNN on the BDD dataset and use this pre-trained model as a baseline. From this baseline model, we apply different methods to adapt domain from the BDD dataset to the Cityscapes dataset. We train CycleGAN to transfer BDD style images to Cityscapes style images. We apply self-learning framework. For our method, we repeat the process for 3 iterations. Curves show that performance increases when the iteration increases. These two figures show that our method outperforms other methods at both SIU and IOU. We aim to address human in the log annotation scenario where the detector receives guidance from the human annotator to run on the right track. So, we propose the interactive recurrent annotation with leverage strengths of both automatic process and human guidance, resulting in low annotation costs. The main advantage of our method is that it allows annotator to easily interfere at any time if a mistake occurs to help the detector work better. Particularly, at each iteration, the human annotator has the possibility to correct wrong or missed detections, producing as accurate bounding passes as desired by the human annotator. The correction is then fed back to the detector through self-supervised training, effectively helping the detector to get back to the right track. We observe that the detector can perform at neighbor frames of trained frames with the same efficiency due to their similarity. Hence, to utilize the strength of the detector at neighbor frames, we propose a novel hierarchical correction module. Instead of correcting video frames sequentially, we propose correcting fixed keyframes in which the frame distance binarily decreases at each time step. It guarantees for obtaining high quality annotations while minimizing annotation time. Our hierarchical correction is more efficient than the standard frame by frame annotation, resulting in faster interactive annotation. We evaluated our proposed framework on the dashcam accident dataset. We used raw video sequences of the accident set. We evaluated our proposed framework against other annotation methods such as manual annotation of all objects frame by frame, using the pre-trained model to generate bounding boxes and then manually correct frames, correcting mistakes sequentially from results generated by ARA and IRA directly using the pre-trained models at the initial detector. Experimental results show that our method takes less time to annotate a video frame. In our framework, human annotator needs to correct the least number of objects generated by the detector. Our proposed framework is 9 times faster than manual annotation. Our method also cuts down to 36% the number of corrected objects. So, our method minimizes both annotation time and human label cost rather than the standard annotation method. Please scan the barcodes for video demonstration and our results. Thank you for your attention.